This is our fifth video out of our AMC series. Today we'll be covering Combinatorics, counting, and probability. Let's get started. First is Combinatorics. Combinatorics is a branch of mathematics concerned with selecting, arranging, constructing, classifying, and counting or listing things. So now we're going to go on to probability. There's a few terms you need to know to be able to solve probability problems, so we're just going to go over those. First one is experiment, then outcomes or sample space. Probability of the desired event is P. The number of all possible outcomes is N. The number of distinct ways or outcomes the desired event can occur is M. And P is equal to M over N, meaning probability is equal to the number of distinct ways or outcomes over the number of all possible outcomes, meaning probability is equal to desired event over total outcomes. So our first example in probability. So in this example, the question is, when tossing a coin, what is the probability of it landing on heads? So here, the experiment is tossing a coin. All possible outcomes is either heads or tails. The desired event is a coin landing on heads. So the probability of the desired event is 1 over 2, heads over total. Now our second example is, the question is, when tossing a dice with 6 faces, what is the probability that you will get an odd number? So here, the experiment is throwing a dice with 6 faces. And all the possible outcomes is getting the numbers 1 through 6. The desired event is getting an odd number. So the probability of the desired event is 3 over 6, because 1 to 6, 1, 3, 5, odd numbers. So 3 out of 6, which simplifies to 1 over 2, or 1/2. Our last example for probability. In this example, the question is, when hitting randomly inside this target, what is the probability that you will shoot inside the small circle? So here, our experiment is randomly shooting at the big circle, or this whole thing. And all possible outcomes is hitting the target anywhere inside this big circle. But the desired event is hitting the target anywhere inside the small circle. So the probability of the desired event. So basically, our total outcome is going to be anywhere inside the big circle. You can shoot anywhere. And that's nothing but the area of the larger circle. And as a radius, we can see here, the radius of the larger circle is 3 inches, and of the smaller circle is 1 inch. So the area is going to be 9 pi, because pi our square formula. And then here, same thing, area, radius is 1 inch, so it's 1 pi. And then, so that with that, we're left with 1 over 9. So now, counting and probability. So the notion of probability arose from games of chance like lotteries, bingos, and roulette. Its basics can be learned using principles of counting. The addition principle. If we have X ways of doing something and Y ways of doing another thing, and we can't do them at the same time, there are X plus Y ways to choose one of those actions. An example is, on a typical Saturday evening, Jill either watches a film or a play. This week, there are 4 movies on the charts, and the theatre has 3 plays. In how many ways can Jill spend her evening? So she can either watch one of the 4 movies or see one of the 3 plays. This is addition principle. So we do 4 movies, 3 of the plays, and get 7. The multiplication principle. Suppose that a task can be done in 2 parts. If the first part can be done in A ways and the second in B ways, then the task can be performed in a total of A times B ways. An example is, suppose that all the roads from city A to city C pass through city B. So, just going to draw a couple of examples. There are 3 paths from city A to city B, 1, 2, 3, and 4 paths from city B to city C. So we're just going to add one over here. How many paths are there from city A to city C? Now, we need to go back to the multiplication principle. Here, if a task can be done in 2 parts. The first part A ways, the second part B ways. So, from going from city A to city B, there's 3 different ways to do it. City B to C, 4. So the answer, you do 3 times 4, 3 times B, you get 12. There's 12 ways to get from city A to city C. Sample space and events. So let's consider an experiment that can produce various outcomes. For example, rolling a dice. The set of all possible outcomes is called the sample space, S, of the experiment. So in this experiment, rolling the dice, the sample space is the numbers 1 to 6. Elements of the power set PS of the sample space are known as events. So our sample space, our set, is the numbers 1 to 6, of which each are known as elements or events. Now, the classical definition of probability. Given event A, the probability of A is equal to the desired event over all possible outcomes. So if events A and B cannot occur simultaneously, they are called mutually exclusive events. Okay, next example. So what is the probability that a randomly drawn positive factor of 60 is less than 7? To find this out, we're first going to need to know the factors of 60. They're listed right here. 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, and 60. You can see how they group together. Okay, so they're asking what is the probability that a randomly drawn positive factor of 60 is less than 7. The factors that are less than 7 are these, just the numbers 1 to 6. So there's a total of 6 factors that are less than 7. So the probability is 6, the desired event, over the total, all possible outcomes, which is 12. There's a total of 12 numbers here. 6 over 12, and this simplifies to 1 over 2, 1/2, which is E. Next example. In a room, 2/5 of all the people are wearing gloves, and 3/4 of the people are wearing hats. What is the minimum number of people in the room wearing both a hat and gloves? So, gloves, 2/5 of the people, and hats, 3/4 of the people. So we want to find the minimum number of people. So to do this, we're going to find the least common multiple, or LCM, of both these denominators. So the LCM of 5 and 4 is 20. So we're going to say that the number of people in this room, the minimum number of people in this room is 20. So total, 20. So if we think 20 are total, then 2/5 of 20, there is 8 people wearing gloves, and 3/5 of 20, there is 15 people wearing hats. This totals up to 23. But the thing is, we only have 20 people, so there can't be 23. So that means there's 3 people wearing both a hat and a glove. So the answer is A. Next example. Suppose m and n are positive odd integers. Which of the following must also be an odd integer? We have our possibilities. So this is a problem where we're going to do process of elimination with our multiple choice answers. So in these type of problems where you have variables, it's easiest to fill the variables with the smallest integer possible that fills the requirements. So we need an odd integer. So because 1 is the smallest odd integer, we're going to use 1. So m and n, we're going to substitute for 1. So here, if we substitute m and n for 1, we get 4. This is an even answer, so this is not our answer. Here, we get 2, so B is not our answer. Here, we get 6, C is not our answer. Here, we get 16, so D is not our answer. So we know E has to be our answer, but it's always best to check and make sure. But here we see E gives us 3, which is an odd number, so we know E is our answer. Next problem. A certain calculator only has 2 keys, +1 and ×2. When you press one of the keys, the calculator automatically displays the result. For example, if the calculator originally displayed 9 and you press +1, it would display 10. If you then press ×2, it would then display 20. Starting with the display 1, what is the fewest number of keystrokes we need to reach 200? Hint. Start from the end and work backward. So we're going to work backward. But to work backward, we're going to need to put these backward or opposite. So the opposite of +1 is -1. So that is one of our keystrokes. And the opposite of ×2 is divided by 2. So that is one of our keystrokes. So we're going to start from 200. So 200, we're first going to divide by 2 and get 100. That's a keystroke. Then divide by 2 again and get 50, a keystroke. Then divide by 2 again and get 25, it's a keystroke. Then because 25 is odd, you subtract 1, 24, divide by 2, 12, divide again by 2, 6, divide again by 2, 3, subtract 1 because 3 is odd, 2, subtract 1 again, and 1. Total of 9 keystrokes. And if you'd like, you can, when you have 2, you can divide by 2 and get 1. So, same thing, in the end, you have B, 9 keystrokes. Next problem. Barry wrote 6 different numbers, 1 on each side of 3 cards. So, very important for this problem is that they are different numbers. And laid the cards on a table as shown. The sum of the 2 numbers on each of the 3 cards are equal. The 3 numbers on the hidden sides are prime numbers. What is the average of the hidden prime numbers? So because this is prime numbers and prime numbers are odd and 44 and 38 are even, we know that our sum is going to be an odd number. And as 59 is odd, we need to give an even prime. As the only even prime is 2, other side is 2, and this is a total of 61. Is our total. So that means 44, has to be 17, which is prime, and 38 has to be 23, which is also prime, to get 61. And it's asking, what is the average of the hidden prime numbers? So average is equal to 17 plus 2 plus 23 over 3, which is equivalent to 14, and over here B is 14. Next problem, we're almost done. A box contains gold coins. If the coins are equally divided among 6 people, there are 4 left over. If the coins are equally divided among 5 people, 3 coins are left over. If the box holds the smallest number of coins that meets these 2 conditions, how many coins are left when equally divided among 7 people? So over here, when divided by 6, remainder 4. That means you need to add 2 to make this totally divisible by 6. Same here. Divide by 5, remainder 3, add 2. So now we're going to find the LCM of 6 and 5. As we all know, the LCM of 6 and 5 is 30. And from this 30, we're going to subtract this 2 and get 28. So we said this is the minimum number of coins in this box. And the question is, how many coins are left over when equally divided among 7 people? As 28 equally divides among 7, 4, 4, 4, our answer is A or 0. Okay. A fair 6-sided die is rolled twice. What is the probability that the first number that comes up is greater than or equal to the second number? So when you roll a dice twice, there is 6 times 6, or 36 total outcomes. But out of these 36, 6 repeat. 1, 1, 2, 2, 3, 3, and on. So there is 30 ways after that. So here, the number of rolls where the first die is greater than the second die is equal to the number of rolls where the second die is greater than the first die. So there's 32 divided by 2, or 15 ways that the first die can be greater than the second die. It can be greater. So now we're going to have the 15 ways it can be greater, plus the 6 ways it can be equal to, over the total number of outcomes, because probability is desired event over total outcomes. This is equal to 21 over 36, which simplifies to 7 over 12, or D. Thank you for watching. Our next session will be our concluding session. In that session, we'll be covering statistics, logic, sequence, series, and we'll be sharing some concluding tips. So thank you for watching, and we'll see you next week. Bye!
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email but without the info and the end.